All right, hello chemistry students. I am your guest teacher today, Mr. Jeffers. I decided to help out Mr. Hendershot and Mr. Bishop because they were so gracious enough to let me to do so. So I'm going to help you out with our Capa problem here. It looks like on this one we are trying to figure out the volume of ammonia that is needed to react with 36.77 liters of oxygen at standard temperature and pressure. Now for your problem, if you're doing this one, you should have the exact same reaction. It's just ammonia with a little bit of oxygen producing basically nitrogen monoxide and a little bit of water. So that's your equation right there. It should be the same for you, but you probably will have different numbers. So we'll start here with what we have so quickly. And we know that standard temperature and pressure is going to mean that we have 1 atmosphere of pressure. That's always going to be the same. And we have a temperature of 273.15 degrees Kelvin. That is always going to be true for standard temperature and pressure. And then moving on, the next thing I recommend you do is define the variables that you're given. So if we look back to the problem, we know that we were given 36.77 liters of oxygen. So we know the volume of oxygen right here, and I've written it out. And we know that we are trying to find the volume of ammonia needed to react with that much oxygen. So we know what we have and we know what we're looking for. The very next thing you need to do is use your ideal gas law equation, which is PV equals nRT. We know we have pressure, volume, moles is in, and then we have our R value, which is always a constant, and our temperature. So all we've done here is standard temperature and pressure. We have 1 atmosphere. Then we've plugged in our volume of oxygen, which is 36.77 liters, and that is going to be equal to N, which is what we're solving for. We need to figure out the number of moles because we have to do a mole ratio later to figure out how many moles of ammonia are needed. So we're looking for N. We have our R value, which is always going to be the same for, if you're for standard temperature and pressure, it's always going to be the same, so it's 0.08206. And then finally, it's going to be multiplied by our temperature of 273.15. So to solve this whole thing, I would highly recommend you multiply your R value right here, multiplied by your temperature value. Once you get that, you can divide this, because remember, we want to get N by itself, so we'll divide everything by these two multiplied together. And then realistically, it's going to be 36.77 divided by these two numbers multiplied together, and you should get 1.6404 moles of oxygen. So that is how many moles of oxygen we have here. The next thing we have to do here is, if we know how many moles of oxygen we have, we can do our mole ratio to figure out how much ammonia is needed. So in the chemical equation, we know that you need 5 moles of oxygen for every 4 moles of ammonia. So when we plug this in here, we're going to put our starting value of 1.6404 moles of oxygen. We know that to cancel these out, we need to have oxygen on the bottom, so we'll put our 5 moles of oxygen. That's just the coefficient in front of oxygen in the equation. And then we are going to have 4 moles of ammonia here. So realistically, when this is all said and done, you're going to do 1.6404 multiplied by 4, then divide that whole thing by 5, or you could just do this number multiplied by 0.8. That's just 4 divided by 5, so you can do this number multiplied by 4 divided by 5, which is 0.8, and you should get 1.3123 moles of ammonia. You should get a little bit lesser value because remember, 4 divided by 5, that's 0.8. If you multiply by a decimal, you should get a smaller number. So this is how many moles of ammonia we have. And then lastly, if you know how many moles of ammonia you have, we will go back to our ideal gas law equation and we will plug everything back in so we can figure out our volume. So down here, I've replugged it back in. Remember, we're still at standard temperature and pressure, so it's still 1 atmosphere is our pressure. This is our moles of ammonia right here, what we just calculated. This is our R value, it's still the same value, and this is 273.15 degrees Kelvin, still the same value. So at this point, all you really have to do is multiply these 3 values. Technically, you do divide by 1, but it doesn't really matter because anything divided by 1 is not really going to change your answer. So realistically, just multiply these 3 values, and you should get that 29.416 liters of ammonia are needed to react with 36.77 liters of oxygen. So this is our final answer for this one. So there are a few steps here that kind of make it seem a little bit more complex than it really is, but now I'm going to show you a quicker way of doing this. So we just found out that this is our final answer. This is how much ammonia we need for this problem to react with 36.77 liters of oxygen. But if we look at this problem a little carefully, realistically, when we were solving for N, this is our R value and this is our temperature, we divided everything over here by these two values, so we divided right here, but then when you come all the way back down here, we multiplied by these two values. So multiplication, division here, and then multiplication here, they are technically opposites of each other. So realistically, this is just an extra added step that we do not have to do. They cancel each other out. So what we can do here is we can actually go through, erase my work here. We can actually go through here and we can just do a mole ratio, because we're given a volume of 36.77 liters, and then we're trying to find another volume value of ammonia. So realistically, all you have to do here is say that, well, if you start with 36.77 liters of oxygen, you can just do the mole ratio. We can just immediately start to do the mole ratio. And we know from our problem that there are 5 moles of oxygen for every 4 moles of ammonia. And that's actually all you have to do for this problem. Is we just have to realize that you can just do the mole ratio here, because you're going from liters and then you're going to end with liters as well. So that's all you have to do for this problem. So realistically, we can do this. If you times by 0.8, you should actually notice that you get the same answer of 29.416. So it's the same process, just with skipping the unnecessary steps. You can do either process, whatever is easier for you. You can take the long route if that makes you feel more comfortable, or you can try this trick if that helps you as well.
And 1.
Hey chemistry students, just wanted to preface this with, I miss you all very much. The coronavirus cannot get rid of me that easily. And please bear with me, I do not have an act for the camera, such as Mr. Hendershot himself. So let's take it away with part B of question 13. We were given 7.243 grams of oxygen, O2 in our case. Anytime oxygen by itself is O2, it's a diatomic molecule. And we need to figure out how many liters of nitrogen monoxide gas we can produce with that many grams of oxygen. So first thing, let's go ahead and take this grams of O2 and let's put it into moles of O2. So 7.243 grams of O2, and then the molar mass of O2 is 31.998 grams of O2 per moles of O2. And since grams was on top here, grams has got to be on bottom here. And that comes out to 0.226 moles of oxygen gas. So now we're in moles of O2, and we still got to get to liters of NO. But what's the molar ratio of oxygen gas to nitrogen monoxide? If we look at our equation that's written out for you on Capa, the ratio for oxygen gas is 5 to 4 when oxygen to nitrogen monoxide. So since moles of oxygen was on top, 5 moles of O2 on bottom, and 4 moles of NO on top, and our ratio tells us that we're going to produce 0.1808 moles of nitrogen monoxide. So now we have moles of nitrogen monoxide, and we go back to our ideal gas law, PV equals nRT, and we're still at standard temperature and pressure, so that's 1 atmosphere at 273.15 degrees Kelvin. So 1 atmosphere times V, that's what we're solving for, volume, is equal to the moles that we just solved for, moles of NO, 0.1808 moles of NO times our R, which is constant, always going to be 0.08206 times our standard temperature, which is 273.15, and this works out really nice. Since this is a 1, we can ignore that and just multiply these 3 numbers by themselves and get 4.0526 liters of nitrogen monoxide. Thank you.
Go.
Alright, another thing we want to note too, because we're not going to do a demonstration for the next 2 problems, is that this is asking for the mass of water produced. So you're going to take your liters of nitrogen monoxide and you're going to eventually convert it to moles of water after using the PV equals nRT, and then you have to use the molar mass to convert from moles back to mass of water. And then for part D, we're still in standard temperature and pressure, and it tells you milliliters of ammonia. So really quickly convert that to liters of ammonia before you go plugging that into your equation.